Let's finish the wrap-up of application exercise 3-4. We talked in class about how to fill in this table given just information on the wage rate and on the cost of capital. I calculated the marginal product, just the change in output divided by the change in labor input. Then we talked in class about fixed costs just come from our given fixed costs. Variable cost is this wage rate times the number of hours we're employing. Total cost is the sum. Average cost per bat, it's undefined when output is 0, but otherwise it's the average fixed cost is the total fixed cost divided by output. So the key thing as we move to discuss costs is we're keeping track of how costs change with output, not anymore with labor. And then finally, the marginal cost per bat, where technically this 3 is the marginal cost as we move from output of 0 to output of 5. So you're going to see when I graph this, I'm going to map marginal cost at the midpoint between the starting output and the end output. But for our purposes, just mapping it at the ending output is fine. Anyway, that's how you do the table. I asked you in the in-class application, though not I see on the worksheet, to graph the average variable cost, average total cost, and marginal cost. I'm going to do it 2 ways. We are given in the information that Acme Sporting Goods is Paducah's only customer, and it pays Paducah just a flat fee of $10 per each finished bat. So our output rule should be produce one more bat as long as that $10 price is greater than the marginal cost of a bat. So should we go, we only have output increasing in 5. Should we produce 5 bats? Yeah, the marginal cost is $3 a bat. We can turn around and sell those for $5 a bat. You bet. Again, should we go to 10? Yep. $10 is higher than $3. Should we increase output to 15? Absolutely. It costs us $6 a bat to get $10 a bat. That's a good deal for us. Should we increase output to 20? Yeah. Even spending $9 to make a bat makes sense if we can turn around and sell it for 10. However, increasing output to 25 would not be wise. It would cost us $12 a bat to turn around and sell it for only $10. We'd be losing money with every bat, and we wouldn't do that. So our answer, by just looking at this table, is produce 20 bats if we care about maximizing profits. Now, graphically, we can do the same. Tabular, with the tabular information, we'd have to recalculate our marginal costs, and they just go up by 2. 5, 5, 8, 11, 14, 17, this is 17, and 20. And notice here, our profit maximizing output level would shrink from 20, according to this tabulated information where we're just jumping by 5s, to 15. In the graph, it probably was probably a little worse. Here I've done that by means of an Excel spreadsheet graphing function that's sort of nice. I did plot this marginal cost. You can see the legend here, the marginal cost at the midpoints of the beginning output and the ending output. So a couple things to note about this. When you graph these curves correctly, the marginal cost will always intersect the average total cost and the average variable cost at the minimum of those functions. The other thing to know, you might wonder, where are average fixed costs? We care about those too. Notice that we have information on average fixed costs. Average total costs are the sum of average fixed costs and average variable costs. That means the vertical distance between average variable cost and average total cost tells us average fixed costs. And we notice that starts big as output is small and then gets steadily smaller. So we will see, if we're mapping things correctly, our average variable cost is asymptotically approaching the average total cost. Early on, average fixed costs are big. As output goes to infinity, average fixed costs go to zero, and that means the vertical distance between average variable costs and average total costs also go to zero. Anyway, here's our graph. This set of curves is the way we're going to represent the short-run production and cost problem for firms in general throughout the rest of the course. Marginal cost in the short run rises because of diminishing marginal returns. There's some fixed factor. We're adding more and more variable factor to some fixed factor, and that results in this increasing cost phenomenon in the short run. Cost increases, marginal cost increases with output. We'll leave it at that. All right, let's go back to the handout. How many bats should Paducah make if its only goal is to maximize profits? Let's do that by the table, and then let's do that by the graph. So you know, graphically, if we're getting $10 a bat, our demand curve is just a flat line at D naught. And there, the profit maximizing output level, well, can I get rid of that? Yeah, the profit maximizing output level is where marginal cost and price intersect. And here we get an answer of 19, not 20. But that's also an artifact of having shifted this marginal cost curve. Actually, I shifted it back a little bit. It should be, I shifted it, if I plotted it on each point instead of the midpoint, this would be over here. We would have gotten something like that. Anyway, we would have gotten 21 instead of 20. Anyway, the table only gives us outputs in fives, so we can't really answer 19, but our graph indicates actually that 19 would be the profit maximizing. So if you presented the graph and mapped it so carefully to scale and gave an answer of 19 supported by this kind of graph, I'd give you full credit. If I didn't give you full credit right out of the gate, that's one you could bring up to me later and say, hey, look, I did it this way and it makes sense, and I would agree with you. All right, that's that one. Oh, no, we've got some more to do. The problem goes on. What would be the profit maximizing number of bats if the government imposed a tax of $10 a day on the company? And the key here is to recognize that a tax of $10 a day would be an increase in the company's fixed costs, and that would reduce profits, but it wouldn't affect output. So let's just back up a little bit. Notice that at 19, average costs at 19 are, $8.25 or so, $8.10, give or take. And so we're making $1.90 per bat at $1.90 times 19. I don't know, 360, something like that, 370. Anyway, we're making some. Let's see, $1.90 times 19 would be 37. I missed a decimal place there. In order off by an order of magnitude. Anyway, profits at 37. So a $10 tax would shift up our average cost curve by some amount, and our profits would certainly be lower. Should have done that in a different color. But because our marginal costs didn't change, the point where price and marginal cost intersect is still the same. So our profit maximizing output is still the same. So that's the key to number 3. Now, on the other hand, if the profit maximizing number of bats, if there were a $2 per bat tax, then our profit maximizing number of bats would change. So let's do that both with the table of information and with the graph. Different than that. Let's check. everywhere the marginal cost curve would be $2 higher. So it would be, let's just map a couple points. Each would look like that. So our profit maximizing output looks like it would fall to 16 bats from 19 bats. It's a little more precise to do it by the graph in this case. Anyway, output would fall. If you did it by the table and you said output would fall to 15, that'd be fine. If you did it by the graph and said output would fall to I said 16 and I wrote 19. Output would fall to 16 bats by the graphical analysis. And why do the taxes in Part 3 and 4 have such different effects? Simply put, the tax in Part 3 affected only fixed costs, and fixed costs are our output rule, set output where price equals marginal cost, has nothing to do with fixed costs. So the change in fixed cost didn't make a difference. In Part 4, however, the tax changed the marginal cost. Marginal cost went up by the $2 tax. You could map it as the price that the company receives as falling to 8. That would be perfectly equivalent, would get you exactly the same answer. There's another one where either methodology would work fine.